Hi, everybody. So today we're going to look at ions and ionic compounds. This is going to be important for the lab tomorrow when we talk about minerals and salts, but also just an important, again, kind of basic idea of how we communicate chemistry and how we talk about these compounds. So up until this point, we had mostly been talking about covalent compounds, which were the kinds of bonds like this, or we drew a line and we talked about that as being two shared electrons. And just to review, the name for that is a covalent bond. But lots of compounds don't do that, don't bond in that way. So the other way that a lot of molecules can bond, can connect, can form compounds is by making ions. And so if you recall back to the last module, we saw some examples of things like this, where you'd have a chemical symbol and then a charge on it. So this is magnesium with a charge of +2 or 2+. You can use those interchangeably. We usually put the number first just because it's a little bit clearer, but what that really means is that there are two positive charges on this magnesium particle, which makes it an ion. So just to review our terminology again, when we say atom, we're referring to something that has a neutral charge. And in terms of the subatomic particles, this means the same number of protons and electrons. And remember, protons are positively charged, electrons are negatively charged. So if we talk about a magnesium atom, it is element number 12 on the periodic table, which means it has 12 protons. And so a neutral magnesium atom would have 12 protons and 12 electrons. So let's take away the charge here. We've got 12 protons and 12 electrons in a neutral magnesium atom. And this is one of the examples from the front page of that atoms activity from module 2. So if you want to go back and review that, that kind of goes through this stuff as well. So if instead we have a magnesium ion, magnesium 2+, what's the difference? Well, it's got two extra positive charges, but that does not mean that we add more protons, because again, if you remember from that activity, the number of protons determines the type of atom that it is. So if we add more protons, we'd have 14 protons, which would actually make it silicon instead of magnesium, because it would be number 14. So this still has to have 12 protons. The way we get that positive charge is by taking away electrons. So a magnesium 2+ ion is only going to have 10 electrons instead of the 12 in the neutral atom. Right? So this is a magnesium atom, and this is a magnesium ion. Ion meaning having a charge. We can also have negative charges, so we can have things like a chlorine atom, which would have 17 protons and 17 electrons. And then chlorine actually makes a -1 ion, which is 17 protons and 18 electrons. Right, so we've got an extra electron there. All right, so we can have positive ions, negative ions. There was some terminology from that also on that atoms activity. So all of this should pretty much be reviewed at this point from that worksheet. But just to remind ourselves, a cation is an ion with a positive charge, and an anion is an ion with a negative charge. Okay. So now we have reviewed some of the stuff about the basics of what ions are. So now we can talk about what does it mean for ions to form a compound, to have multiple ions together, they don't form a compound like a covalent thing. So we don't show ions connecting to each other in this way because they're not sharing electrons. So this line thing doesn't really make sense when we're talking about ions. If we want to talk about a compound between magnesium ion and chloride ion, then we need to just kind of look at the charges, because really what's happening in an ionic compound is it's just a pure negative positive attraction. So there's nothing like chemically with the electrons being shared between these two atoms or anything like that, or these two ions. All that's happening is you have a positive one, you have a negative one, and they attract each other. And so it's just this attraction. And that's why we don't use that line to show them, because they're not really being connected in the same way as, let's say, carbon atoms were in the structures we saw over the last couple of weeks. So instead, what we have to do is make an overall neutral compound out of magnesium and chloride. Magnesium is a positive or a +2 charge, and chloride has a -1 charge. And so what that means is that if we simply put them together, 1 Mg and 1 Cl, then we wouldn't have an overall neutral charge for the compound. We would have extra positive, right? We'd have Mg having a 2+, and we'd have Cl with the -1, and so you'd have a +1 left over. So we don't want to do that. So instead, we have to put them in a 2-to-1 ratio so that the overall positive charge is +2 and the overall negative charge is -2. +2 -2 makes neutral. So a neutral ionic compound of magnesium and chloride would have twice as many chloride ions as it would magnesium ions. And the way that we express this in a chemical formula is using subscripts. So MgCl2. So notice how this is a little bit different. In the covalent compounds, the formula describes exactly how many of each type of atom are in there, right? We saw those types of things. If you saw a formula that said C4H8O, that means that it would be a molecule with 4 carbons, 8 hydrogens, and 1 oxygen. Ionic compounds are a little bit different. MgCl2 does not mean there's 1 magnesium ion and 2 chloride ions. It means that these things exist in a compound in a ratio of 1 magnesium to every 2 chlorine, or 2 chloride to every 1 magnesium. So an ionic compound is actually just a big packing, in the solid state anyway, it's a big packing of a bunch of these things all together. And so they're packed together in a ratio of 1 to 2. So we use those charges to figure that out and to put those things together in the compounds. So let's try that first, and then we'll talk about how we actually figure out what the charges are after that. So one thing that we can do now is I could give you a name of a compound, of an ionic compound, and you could maybe figure out how to put that together in a formula if I gave you the particle. So let's look at molecule, or the not molecule, the ionic compound, sodium chloride. All right, sodium chloride is going to be made up of sodium ions, which is Na+1, and chloride ions, which is Cl-. We already saw that one. All right, so then the question is, how do we make a compound of those two? Well, we do it in a 1-to-1 ratio, because this time we have +1 and -1. So we don't need to adjust the numbers to have an overall neutral compound, and so the formula would be NaCl. All right, let's look at another example. Calcium oxide. So calcium is Ca+2, and oxide is oxygen, or O, -2. So we have 2+, 2-. So when we put those together in a compound, we just have CaO. We don't need to adjust the numbers at all. All right, let's try another one. Sodium nitride. Sodium's Na+. Nitride is N minus 3. So now we've got 3 minus. So if you're watching this later, pause the video here and see if you can figure this out, and then come back and see if you got the right answer. All right, so you're back. Hopefully you got a chance to give this one a try. Since we have +1 and -3, how do we adjust these so that overall we have a neutral, we have as much positive as we have negative? Well, we do that by adding 2 more sodium. So now we have 3+ total between all 3 of those to balance out the 3- of the N3. And in a formula, that's going to look like Na3N. So your ionic formula for sodium nitride is Na3N. All right, so these are the basics of how to do that. But then you might be asking, well, how do you know, like when you say sodium, how do you know it's +1 and not +2? Or how do you know calcium is +2 and not +3 or +1 or something else? So that's what we're going to talk about now. All right, determining ionic charges. So how do you actually figure out what the charges on these ions are? And the answer is there's a couple different answers actually. The easiest way to do it, or the easiest way that you can sometimes do this, it doesn't always work, is that there are some ions there are some atoms that always make the same charge, and so those are very predictable, and they happen to be in certain locations on the periodic table. So I'm going to draw a periodic table here. Okay, just kind of a basic outline of one. And we can split this up into some columns where there are some predictable charges. I should have made these, here, I'll make these lines a little bit thinner so we can fit them all here, because we got to get 5 columns in here. I should have probably made that a little bit bigger, sorry. Okay, that's fine. All right, so up on the periodic table, we've got 1, 2, and then coming over here, we've got 13, 14, 15, 16, 17, and 18. So if you've got a periodic table, you can pull it out and see what the actual atoms are. The reason I divided it up this way is because we can look at which spots in the periodic table have these predictable charges. For example, everything in column 1 gets a +1 charge when it becomes an ion. So that would be hydrogen, lithium, sodium, potassium, rubidium, cesium. We don't really worry about the radioactive ones on the bottom because we don't use those for chemistry much. But those are all going to get a +1 ion when they become ions. So a sodium atom is neutral, but a sodium ion is always +1. A potassium atom, K, is neutral, but a potassium ion is always +1. And then to follow that pattern, the next column over, those are all going to be +2 or 2+. So magnesium, calcium, strontium, barium, 2+ whenever we see those ions. So that's really helpful and handy because that's column 1 is +1, column 2 is +2. Pretty easy. Okay, now this whole middle area, that's where it gets tricky. Those atoms mostly have different charges. So for example, iron, Fe, which is right in the middle here, that can be +2 or +3 depending on the compound. So we don't have the luxury of just saying like we know what this charge is. So we're gonna have to use a different idea for that, which we'll get to later. So instead we can move all the way over to the right, and we can actually just sort of cross out column 18 because we don't really make ions from those, the noble gases. Our next column over here is the halogens, and those are mostly -1. Then we've got the oxygens column, or the chalcogens, which is -2, and then -3. And really that only applies down to the stair step thing. So if you see that on your periodic table, it goes like this. So we're really only talking about that top half. And then we don't really have a predictable charge in column 14. In column 13, we have aluminum. which is always +3. That's pretty much the extent of it. There are a handful of atoms in the middle here that always make the same charge. Zinc is always +2. Silver is always +1, and so there's a few, but we're not just going to have to memorize the random exceptions. What I would like you to be able to do is just determine the charge from these basic broad categories. So that means that if we see a name like aluminum sulfide, that we should be able to figure out the formula. So first we look up the symbols. For aluminum sulfide, aluminum is Al, and sulfide comes from sulfur, which is S. You'll notice here and earlier that when we talk about anions usually have a slightly different name from their atom counterpart. So sulfur becomes sulfide, oxygen becomes oxide, chlorine becomes chloride, and so on. Nitrogen becomes nitride. The cations, the positively charged ions, don't change their name. All right, we've got our symbols, aluminum and sulfur. So now we can look at the periodic table and find where those are, and that will tell us their charges, hopefully. In this case, we talked about aluminum, so we know that that one's going to be +3. And then sulfur you can find in column 16 just under oxygen, and that is makes it a -2. So we found the atoms, we found their charges, and now all we have to do is balance them out so that they have an overall 0 charge. Now you might see that's a little bit trickier with this than it was with the previous examples, because we can't only change one of them, we have to change both of them. So we actually have to have 2 aluminums and 3 sulfides to get this to balance out, 6 plus and 6 minus. It's not enough to just change one or the other. So the formula of aluminum sulfide then would be Al2S3. All right, so for these types of atoms, this is what I would like you to be able to do. To look at a name, find the symbols, look up the charges on the periodic table, and then write a balanced formula. All right, then let's talk about what happens when you don't have what we call predictable charges. So what happens with that whole middle range of the periodic table where the atoms can be whatever charge they want to be, the ions can be. Not necessarily, you can't just look up at your periodic table and say, oh, that's in this column, so it's +2. So what do you have to do? Well, in these columns, or for these formulas, these cations, first of all, I guess we should say it only happens with cations. But the other thing to know about this is that those are actually different compounds. So iron chloride with a +1 or +2 iron is a different compound from iron chloride with a +3 iron. And so that actually needs to be specified in the name if we're going to know which type of charge we're talking about. So what that means is when we see a compound name, we're not just going to see iron chloride, we're going to see iron with a number in parentheses and then the anion name. All right, and so this number in parentheses tells us the charge on iron, and it's always positive. So now we can write down our symbols, and we can say, all right, Fe, and it's 3 plus because that number in parentheses told us that we're talking about iron 3 here. And then chloride is the same chloride we've been talking about before, -1. So our compound is going to be 3 chlorides for 1 iron, or FeCl3. Notice that the 3 in parentheses is not the subscript on the iron. In this particular compound, it ends up being the subscript on the chloride, but that's just because this happened to be a -2 anion. That's not always going to be the case. So look, for example, copper 2 oxide. We'll try that one. So copper is Cu. Oxide comes from oxygen, which is O. Now we need to find the charges in order to build the compound. So the charge on copper is given right here. So we know that's going to be +2. The charge on oxygen we can get from the periodic table because oxygen is in group 16 here. And so that's -2. So now we have +2, -2. We don't need to adjust ratios at all. They balance each other. And so copper 2 oxide is CuO. So notice that this compound is called copper 2 oxide. There's no subscript 2 anywhere in there. The 2 refers to the charge on the copper, not to one of the subscripts in the formula. All right. Also, you can notice here that I'm not asking you to go the other way. I'm not asking you to take a compound or a formula and then go back and tell me what the name should be. That's a little bit trickier of a skill because there's different ways that these compounds can be named, and so we're not going to do that in this class. But what I do want you to be able to do is take a name like this and turn it into a formula like this. Okay. Our last category that we have to talk about is the polyatomic ions. Water here. All right, so there's another class of ions that aren't just one atom. Notice all the ions we've talked about so far up here are all just one atom. So, you've got Ca, O, Na, N, Al, whatever. But there's a class of ions that are actually multiple atoms covalently connected together that all together make an ion. So here's an example of one that we've actually used in lab, hydroxide ion. Hydroxide ion is OH and it has a negative charge. So that means that there's this, we think of it as sort of one thing. Technically what it is an oxygen atom and a hydrogen atom covalently bound together. So sort of like 2/3 of a water molecule. And then that overall has a negative charge. So when we talk about sodium hydroxide, which is the chemical that we used as a reagent in the biodiesel synthesis last week, that is an ionic compound of sodium, Na plus, and hydroxide, OH minus. And we balance out the charges and get NaOH. We don't have to adjust anything with subscripts. Some other common polyatomic ions, nitrate, NO3 minus, sulfate, SO4 2 minus, polyatomic cation that we will work with called ammonium, which is NH4 plus 1. And this is not an exhaustive list. There's lots of these, but there's nothing you can really figure out with these. Like, if you didn't know that nitrate is NO3 minus 1, there'd be no way to really figure that out from the name. So when you see a polyatomic ion in a name, you just have to know that that's something you have to look up. You can look it up on this table. You can look it up on a different table. It's something that has to be looked up, and you have to look up the formula and the charge. So for example, if we had for our name calcium, let's do nitrate. What did I do? I started some sort of note thing. I don't want to do that. Stop. Stop. Nope, I don't want to do that. How do I make it go away? Okay. Thank you. All right. Calcium nitrate. So we know calcium is Ca, and we can look it up on the periodic table and also know that it's +2. Nitrate, all we can do is say, oh, that's one of those 8. It ends with 8. It might be a polyatomic ion. So I'm going to look it up I'm going to look up its formula on the chart of polyatomic ions. And so for that, this is NO3 and -1. So now if I want to make a compound of those two, I recognize that NO3 is -1, calcium is +2, so I need two of these, two nitrates, to balance out the calcium. So now I've got 2 minus, 2 plus. And so to draw that formula, or to write that formula, I need to show that I actually have two of these nitrate ions. So that's what my formula will look like, Ca and then parentheses NO3, parentheses 2. That's how these polyatomic ions work. Again, you don't have to memorize these, although by the end of the semester you probably will know some because we'll be using them. But when you see them in names, you see them on the chemicals that you're looking up for your SDSs to get prepared for lab, just recognize that if they end in 8 or that's a good clue that they are polyatomic. If there's something that just isn't obviously on the periodic table, like hydroxide, again, polyatomic. Cyanide is another one. It ends in "ide", but there's no cyanide type element on the periodic table, so that one's Cn -1. So you can look it up as a polyatomic ion. So goals for this skill, you should be able to draw or write a chemical formula for an ionic compound given its name, or really just given any two ions. And you should be able to look up the commonly formed ions on the periodic table and use a chart like this to find the formulas of polyatomic ions. So tomorrow in lab, we'll be doing two kind of unrelated but same theme labs. There's the mineral lab, which is properties of minerals, which we'll be dealing with in the classroom. And then there's the Are All Salts the Same lab, where we're going to use a type of analysis called ICP OES, or inductively coupled plasma optical emission spectroscopy, to determine what types of ions are in some different types of salts. We know salt, like table salt, is mostly sodium chloride, but there's other types of trace elements in there as well, and so we'll be able to measure some of these in this experiment tomorrow. All right, let me know if you have any questions or any trouble with this stuff. After class tomorrow, we'll look at polarity and intermolecular forces. So that will be the next live stream. Bye, everybody.